Let's go ahead and get started. Good morning, everyone. Thank you so much for making it to this Q-Chem webinar, which is going to be presented by one of our 2025 Summer at Q-Chem interns, Xinchun, who's here to present her work on constrained CASSCF and type binding in Q-Chem, which she worked on over this past summer to implement in Q-Chem. So a little bit about Xinchun herself before we get started. She got her BSc in chemistry from the University of the Chinese Academy of Sciences in 2020, and she's currently working in Professor Joseph Botnick's group at Princeton University on her PhD work, which is in electronic structure method development. And currently, she is working on developing a new electronic structure method called constrained CASSCF, CASSCF for short, which she will be talking a little bit about in her talk today. And the point of that method is to kind of capture the charge transfer excited state. And she actually did an internship with us this past summer over the last couple of months at Q-Chem here in the Q-Chem office to enable type binding calculations in Q-Chem and implement the constrained CASSCF method that she's going to be talking about. So we are really excited to have her here. And we were absolutely delighted to have her here over the summer. She did some really wonderful work, and we are really excited to have her present some of this work to y'all. So without any further ado, I will go ahead and hand this over to her.
Thank you, Shannon, for the really nice introduction. So I will first share my screen. Can you see my screen now?
You can see it perfectly. Thank you so much. Yes.
Oh, okay. Good morning or good afternoon, everyone. Thank you so much for coming. Today, I'm going to present my work during my intern in Q-Chem this summer. Basically, I was working on implementing constrained CASSCF, which is a new electronic structure method in our group that helps to simulate the charge transfer excited state. And I was also working on enabling tight binding feature, which helps to introduce some semi-empirical parameters into the Q-Chem SCF calculation loop. And I would really appreciate your feedbacks. So in both parts of the talk, I will start with the motivation of these two methodologies or features. Then I will dig a little bit into the technical details, as people might be interested to know how we actually implement those features inside the Q-Chem framework. And I also hope this can help people understand more about the Q-Chem infrastructure. Lastly, I will show you some results using these two very powerful techniques. In the end, I will tell you about some of the ongoing work and future directions in our group. So before we dive into the detail of the methodology, let me first introduce the model problem that our group is interested in working on. A molecule sitting on a metal surface is a very common system in chemistry and physics, which could represent many electrochemistry and catalysis reactions. For example, in this electrolyte cell, the electrolyte is surrounded by the electrolyte solution. Therefore, it can be represented by such an abstract figure where you have a molecule or say an impurity sitting on a metal base. We are very curious about the electron transfer between the molecule or impurity and the metal surface, so that we can really simulate many interesting chemistry happen on the electrode. So when developing a new method, as people always do, we choose to start from the simplest possible system that one can think of. So we choose the lithium chloride because lithium is the simplest metal and is very widely used in battery materials. And chloride is a highlight item which has a large electronegativity. Therefore, it would be a good system for us to do a proof of concept and study the electron transfer between those two fragments. Consider we move the chloride atom closer and closer to the lithium. At the beginning, when they are far separated, both the lithium and chloride will be neutral, as shown in the left-hand side of the equation. And as the lithium and chloride goes closer and closer, the lithium cluster will tend to give an electron to the chloride, and then they form an ionic species together. Therefore, we should expect the whole system to undergo an electron transfer process as we change the distance between these two parts. Then the question becomes, how can we describe such an electron transfer process? Some of the very standard approaches are to use the Markov theory or to run some non-adiabatic dynamics such as surface hopping to model such a system. And both of these two approaches will need the information about the diabatic states, which in our case is the ionic lithium plus chloride minus and neutral lithium chloride state. That means we will need to have an excited state that could capture the electron transfer feature, which means we will need to avoid local excitation. And I will explain this point in great detail in the following slides. So this is a very typical picture in the Markov theory. Markov theory and it could represent the electron transfer process. So as you can see here, we have a double whale formed by two parabolas. Each of these parabola, which is the blue line here, represents a charge state. So the left parabola here is the neutral charge state, and the right parabola here could represent ionic charge state. And as you can see, if we change the configuration to move from left to the right, the ground state moves from the neutral species to an ionic species. That's how an electron transfer could happen as we change the configuration. However, those diabatic states, those blue curves couldn't be directly calculated. Instead, in our electronic structure calculations, we only get some adiabatic states from the diagonalization of our Hamiltonian. In order to get those diabats, which represents a specific charge state, we have to do some calculation like Boy's diapotization to linearly combine the adiabatic states to derive a diabatic state. If we want to get some reasonable diabatic states, there are some conditions that the adiabatic states should satisfy. And as we can observe from the graph, if we are very far away from the crossing region, the coupling between the two states is very small. That means the diabatic states are almost the same as the adiabatic states. While in the strong coupling region, which is the middle part, you can see that both of the two adiabatic states can be viewed as a mixture of both diabatic states. Therefore, in our electronic structure calculations, we are expecting to generate some adiabatic states that should have the excited state and the ground state should have different charge characters if they are very far away from the crossing. And in the crossing region, both of the two adiabatic states should have the feature of both charge states. However, if we perform a very standard electronic structure method, it will not be able to generate the adiabatic surfaces that meet our requirement. That is because when we perform a normal electronic structure calculation in a system that contains a metal, since the density of the states from the metal is too large, so there will be actually many Drude states, which marked by the gray lines here. Those states are often represents the metal-metal excitations. Therefore, it should have like the same charge state as the ground state. And it is really hard to pick out the charge transfer state if you get a sea of excited state from normal calculations. So we really want our electronic structure method to automatically pick out the state that we want, which is the state marked red here. And those states should have a very distinct charge distribution from the ground state. So let me briefly summarize the key requirements and how we are able to achieve that using constrained CASSCF. First, to run a dynamics, you need a very reliable and smooth excited state to run dynamics on. In that case, normal Hartree-Fock and ground state DFT doesn't optimize the excited state, so it's not good enough to run excited state dynamics. And the second requirement will be in a strong coupling regime, we need to optimize both configuration that represents the neutral and ionic charge state. Therefore, our method is based on a state averaged version of CASSCF, so that we are optimizing many configurations at the same time. Last and the most importantly, the excited state should really describe a charge transfer state. In our case, that is to say, the excited state should represent the lithium plus chloride minus, rather than just the internal excitation inside lithium. And that was the key motivation for us to come up with constrained CASSCF. And I will address this point in the following slides in great details. Before we introduce the constrained version of CASSCF, let me briefly overview the standard CASSCF approach here. We can start with the easiest CASSCF 2-2, which means there are two active orbitals sitting on there are two active electrons sitting on two active orbitals. In a CASSCF calculation, we divide the whole Hilbert space into three subspaces. The first one is the inactive space. In this space, all of the orbitals are doubly occupied. And the active space, which is denoted by T and U here, in this space, a full CI expansion is considered, and the occupation number of the orbital in the active space could be any number between 0 and 2. And the third subspace will be virtual space, which is totally unoccupied. CASSCF is very similar to Hartree-Fock, except that it introduced this new space, active space, which those orbitals are partially occupied. So if we only consider the singlet, there are only three possible configurations for the CASSCF 2-2. The first one is the left column here, that that shows both of the two active electrons are sitting on the t orbital, which is the lower one in the active space, and the second column represents another configuration where both of the two electrons are sitting on the higher energy active orbital. And in the third case, the spin up and the spin down electrons are occupying different orbitals. One can group those two cases together based on symmetry. So with those three configurations, we can write our CASSCF22 wave function as a linear combination of these three Slater determinants. For CASSCF22 calculations, as you can see, the ground state and the excited state are both linear combination of these three Slater determinants. The only difference is the CI coefficient in front of each configurations. Therefore, if we want the ground state and the excited state to have a different charge distribution, we need to do something to the active space, because this is the only place where the ground state and the excited state has different distributions. So let's focus on the active space. When we consider the system a molecule sitting on metal, we can consider the distribution of the two active orbitals. So there are three cases. Firstly, both of the two active orbitals could sit on the metal. Secondly, one of them could come from metal, while the other could come from the molecule. In the third case, both of them comes from the molecule. But as we all know, the density of states in a metal is much larger than a molecule. So that if you look around the states near the Fermi level, it is highly likely that both of them are, both the LUMO and HOMO are from the metal, because they have a very large density of states, like around the Fermi level. In that case, although our CI coefficients are different, if both the T and the U active orbital are from metal, in those three configurations, the active electrons will always sit on the metal. In that case, we will have similar electron distribution for the ground state and the excited state. And we cannot represent an electron transfer feature in such an electronic structure calculation. So instead of choosing the active orbitals just based on their energy, we can put a constraint to force one active orbital to sit on the metal while the other on the molecule. So this work was first done by my mentor Junhan in a model system, and I later applied it to a ab initio calculation. So first, we can define a projection operator that takes out the impurity or molecule part of the wave function, which is the P operator here. Then we can apply this operator into the active space and calculate the projection of the active space onto the molecule or impurity. We can therefore impose a constraint, say Q equals 0. Q is just a projection minus 1. So this, and we need to satisfy this constraint during our SCF calculation. In that case, this will make sure that one active orbital is always from the molecule. As you can see here, the Q is only related to the orbital coefficient. it has nothing to do with the CI coefficient. So it is only a function of the orbital rotation matrix. After listening to the idea of constrained CASSCF, experts might ask a question like this. What is the difference between the constrained CASSCF and the other excited state method like delta SCF or TDDFT or constrained DFT? The answer is if we compare it to delta SCF, delta SCF usually undergoes the problem of variational collapse. That means although you change the occupation number manually and hope it converges to a saddle point that represents a excited state, it might still go back to the ground state. But in our multi-configuration optimization, we avoid this problem. And delta SCF doesn't specify the charge distribution on each fragment, while CASSCF could guarantee that we can find the electron transfer excited state. And if we compare constrained CASSCF to constrained DFT, we can say that the state average version of CASSCF guarantees that we find orthonormal electronic states with multi-configuration character. While in CDFT, we are actually forcing the electron density on each fragment, and we need to do two separate calculations to get to diabats. That means at each calculation, we are just optimizing a single reference state. And the two diabats are not necessarily orthogonal to each other. And those two diabats doesn't necessarily combine to yield the proper multi-configuration adiabats because they are not optimizing two configuration at the same time. So we have covered the motivation for constrained CASSCF. Let's move on to the technical details of the implementations. So how do we realize the constrained optimization? Unfortunately, there is no constrained optimization class in the Q-Chem libgscf library. So I just rewrote the Q-Chem optimizer to make it do constrained optimization. For example, I modified the LBFGS to a LBFGS constrained version and also for GDMLS. So to do constrained optimization, the most robust approach is to solve a Newton KKT equation. So the L is the Lagrangian here, and the del square kappa kappa is like the Hessian of the orbital rotation matrix. And we also include the interaction between the orbital coefficient and the CI coefficient, which is del square kappa theta here. And we also have the Hessian for the CI coefficient matrix. And the del Q here is the constraint gradient directions. So as you can see, in this equation, we will need the calculation of the CI coefficient gradient and Hessian. We have implemented that in our homemade code, but in Q-Chem, there is no such implementation. So we decided that we want to make the most use of Q-Chem code, so we modified our algorithm a little bit. We take out the CI part and do the constraint optimization first for the orbital part. Then we diagonalize to get the CI coefficient after we optimize the orbitals. But still, to solve the Newton KKT equation, we'll need this del kappa kappa term, which is an explicit expression for Hessian. And this will require a large memory. So what we finally do was to uh, decompose the step into the constraint direction and the long space so that we can merge it into a limited memory BFGF optimizer. Basically, this approach is very easy to implement, but and it works for some of the cases. So first, we need to decompose the steps into the constraint direction and the norm space. And then we will calculate the step in the direction of the gradient of the constraint by the Newton's method. And thirdly, we will use LBFGS to compute the step in the norm space. Then we will perform a step combining both directions. Both.
Oh, I think you cut out for just a second. Can you hear me? Okay. Hang on everyone just for a second. I think we have a little bit of technical difficulties. We will try to resolve that and get right back to you. Can you hear me?
Oh yes, I may share it.
Okay, it was around slide 16 where it cut off. So, okay, perfect.
Can you see now?
Yes. Perfect. Thank you so much.
Okay, I'm sorry. So in the third approach, we basically do not need an explicit caption, and we can decompose our step into the constraint direction and the norm space. First, we can calculate the step in the direction of the gradient of the constraint by a Newton's method. And then we use LBFGS to compute the step in the norm space. We combine these two steps and perform a step which is an addition of these two directions. And finally, we diagonalize to get the CI coefficient. So let me show you the results. First, I would like to show you how the active orbitals look like. If you remember, the T and the U orbital represents the two active orbitals respectively. And the green dots here is the chloride atom, and the purple dots are the lithium cluster. In the first row, it is the normal CASSCF calculation. You can see that both of the two active orbitals are sitting on the lithium cluster. That means we couldn't represent the electron transfer between the ground state and the excited state. But in the second row, after we put the constraint, you can see that in the t orbitals, the t orbital are sitting on the chloride atom, while the u orbital are sitting on the lithium. Therefore, we would have electron transfer described in the between the ground state and the excited state. So now let's turn to the potential energy surface. Here I plotted the constrained CASSCF energy for a series of lithium cluster from lithium 1 to lithium 11 in a CCPV-DC basis. we plotted the state averaged version of energy, which is the green line here. That is the object function we are optimizing. And we are also plotting the ground state and the first excited state. As you can see here, the energy scale is almost the same for all the clusters. That means the bond between the lithium and the chloride is quite localized. And the second take-home message is that the crossing point between the ground state and first excited state moves to larger and larger distance for like bigger and bigger cluster. This is because the ionization potential for lithium cluster is smaller as we increase the cluster size. Besides obtaining the potential energy surface, although we haven't ran a real calculation, we want to obtain some prediction about how an electron transfer could happen. As the chloride goes near the metal surface, there are two possible electron transfer channels. One is the adiabatic channel, which means the trajectory can move adiabatically along the ground state, which is the green arrow, the black arrow here. The other channel would be the diabatic channel, which means the trajectory will hop from one adiabatic state to another adiabatic state in the crossing, but stay in the same diabet. And it will relax electronically when the chloride ion is closer to the metal cluster. So to determine which channel would be the dominant channel, besides the energy gap, the coupling between those states are also very important. So first, we analyzed the diabatic coupling between the ground state and the excited state. So we diabatize using this Boy's diabatization equation, and we got a diabatic coupling curve for the lithium 11 chloride as a function of distance. If you remember, the crossing of the lithium chloride is around 20 angstrom, but this curve peaks at around 6 angstrom. And on the other hand, we also calculated the coupling of the first excited state with those Bass states, which was the addressed state as we plotted before in gray. There are a large number of possible Bass states, and we only consider those that arises from single excitations with respect to these three configurations. And we applied, we compute the gamma coupling according to Fermi's golden rule. And then we got a plot like this. As you can see here, at the crossing point, the gamma coupling is also negligible. So the take-home message of this calculation is that although at the crossing point, the energy gap between the two adiabatic states is very small, but there is a very negligible coupling between both the ground state, excited state, and the excited state with the Bass states. Therefore, we can predict that the second pass, which is the diabatic channel, would be the dominant channel for electron transfer to happen. So far, we have covered the motivation, implementation, and the result for the constrained CASSCF methodology. Next, let us move on to the next part about the tight binding feature. Let me first introduce the tight binding Hamiltonian we use. The main idea of this tight binding Hamiltonian is to treat the bath and metal in different level of accuracy. One only do ab initio calculation in the molecule part, which is the top left part and treat the rest part empirically. So we can divide our Hamiltonian into 4 blocks. The top left part is for the impurity, which is calculated using standard ab initio electronic Hamiltonian. And for the bottom right part, which represents the metal Hamiltonian, it is just a Hubbard model, which has on-site energy epsilon I on the diagonal, and there is a hopping parameter Tij that represents the coupling between nearest sites. On the off-diagonal blocks, which are those green blocks, this is parameterized electronic coupling that represents the coupling between the molecule and the metal, which is parameterized using some amplitudes and the amplitudes of the exponential. So now let me give you our motivation to introduce such a semi-empirical tight binding to Q-Chem CASSCF framework. As you can tell from the last section, right now we could only do constrained CASSCF in a very small number of atoms or electrons. The above method works very well in like 10 or 20 lithium atom, but it's very far from the bulk limit. So we really want to deal with a large number of metal atoms. One approach is to approximate the two-electron part of the two-electron calculation of the large number of electrons and approximate them using some tight binding parameter as we showed before. And the second motivation to introduce semi-empirical parameters is that we could easily change the property of the open quantum bath. For example, in this electrolyte cell, we can simulate the change of the applied voltage by changing the on-site energy in the tight binding model, which is a very common scenario in the electrochemistry study. I will show you some cartoon to illustrate this. Consider the simplest case. Suppose we only have one impurity site, which is the epsilon D here. And these are the on-diagonal elements, which is on-site energy. When it is far below the Fermi energy, we can expect that the electron population in these sites are 2. And as we apply a voltage, we can expect the on-site energy will change because we have a biased potential on that. And the electron population will also change. It will move from 2 to 1. And as we go further, to change the on-site energy to a much higher than the Fermi level, then the electron population will be 0. There is no electron in this impurity site. So I think that could represent many interesting chemistry when we apply a voltage to the electrolyte cell. So now that's why we want a tight binding model in the CF calculation. Now let me tell you how we merge this into the Q-Chem SCF routine. In this model, the challenge is that some atomic sites will have an electron-electron interaction, which is the red part here, while some others do not have electron-electron interactions, which is the green and blue part, but they were all involved in the SCF calculation. This is very different from the QMM calculation, where the MM part is not involved to the SCF calculation. So And in Q-Chem, it is a default that all the orbitals that do SCF is calculated ab initioally. So to extend those calculations to the tight binding model, we will need the capacity to work with two different classes of basis function with Q-Chem, one with and one without two-electron integrals. And to be more general, creating such kinds of two different classes of bases can bring us the flexibility to evaluate different parts of the Hamiltonian at different level accuracy. And this can help us build a bridge between ab initio and empirical model calculation. Although people here are all Q-Chem experts, I would like to introduce a little bit about the Q-Chem libGSCF library in case people don't know about it. libGSCF is the key library in the Q-Chem SCF loop, and it is utilized in almost every Q-Chem job. And in the Q-Chem libGSCF library, there are two main C++ base class. One is a SCF class, and it has many child class like RHF, ROHF, UHF, and so on. So in this kind of class, we basically store all the informations about the objective function, like the basis function, the MO coefficient matrix, the one-electron Hamiltonian, the Fock matrix, the density matrix, and we have some member functions that calculates the energy gradient, Hessian, and for this specific electronic structure method. And the second class would be the optimizer class. Though there are examples like DICE, LBFGS, GDM. So in those optimizer class, we store some variables related to the convergence threshold, the arrow during the optimization. And the most important member function in this optimizer class is the next step function. In this function, it takes in the SCF class as an input and calculated what where to move for the next step by doing some calculation with the energy gradient from the SCF class. And in Q-Chem, those optimizer class are very mature and robust. That is one of the reasons why people favor Q-Chem over other software packages. So we really want to make use of it. So we want to build new SCF classes that could interact well with those optimizer class. So the most naive way is just to duplicate the previous class and make some changes inside of it. So to implement the tight binding feature, first I wrote some API to read in the empirical parameters from input. So this is a new dollar section we created. It reads in the on-site energy of the tight binding model and also the hopping amplitudes. And also we can specify the number of electrons we put in the bath. Secondly, we will build new classes for tight binding model especially. We basically duplicated the original SCF classes and maintain all those member variables and functions. We just change those functions to incorporate in the semi-empirical parameters. And we will also need to modify the dimension of those member functions from the number of ab initio sites to number of ab initio sites plus the semi-classical sites. And then the most difficult part, we will need to rewrite the Fock builder, one-electron Hamiltonian, and so on. So it is very hard to manipulate the dimension in the Fock builder because I noticed that the Fock builder is very well encapsulated in the SCF class. But I noticed that in the Nib-Elmo, the terms in the Hamiltonian are implemented separately, which makes it easier for us to manipulate the dimension. Therefore, I just copied the code from the CASSCF CASSCF generalized Fock builder and use that for the tight binding classes. So for that is the implementation. Then I will show you about the result from this kind of tight binding feature. This is also calculation done by Junhan. We are performing the tight binding calculation in a SF6 model, SF6 plus Bath model. This system contains SF6 sitting on a tight binding metal surface, and the system contains 300 metallic sites, which are hexagonally closely packed in 3 layers, and each layer consists 100 sites, and each metallic site have one positively charged nuclear charge and a localized Gaussian orbital. So we only do the electron-electron interaction ab initioally inside the SF6 metal, and the bath part is treated as treated using the tight binding model. So in this picture, we showed the potential energy surface as a function of the SF6 bond length. We can see that there is a double well for the ground state, and there is a charge transfer occurred at 1.559. And SF6 is neutral on the left-hand side and will be negatively charged for a larger bond length. And we also compared the calculation time on one CPU using the tight binding sites versus using the ab initio sites. We can see that there is a significant, maybe like 20 times speed up if one uses the tight binding Hamiltonian to simulate such a system. To summarize, we have implemented those new features inside Q-Chem. In our homemade code, we were only able to do constrained CASSCF22. Thanks to the legacy CASSCF code in Q-Chem, we are able to do constrained CASSCF for any number of active orbitals and any number of electrons. And in Q-Chem, there was no state averaged version of CASSCF, so we also implemented that. And with Q-Chem code, we are able to extend constraint Cas22 to constraint, sorry. And lastly, we also enabled the tight binding version of ROHF, and CASSCF and constrained CASSCF. So here is some of the ongoing work. Firstly, we will try to further improve the optimizer, and we might consider to combine it with GDM-QIS, which is the best performing algorithm when we initially code up the constraint with a penalty function. Secondly, we are thinking of good ways to input the semi-empirical parameters so that we can meet the needs of different models. the third project would be try to reproduce our previous ab initio lithium cluster calculations. We want to derive some tight binding parameters through linearization, and then to see if the constraint CASSCF calculation could be extended to a bulk limit. And if you are interested, you can refer to those papers for more detailed derivation and mathematical calculations. With that, I want to thank people in our group, especially Joe, Junhan, and Tian for their support. And I would also want to thank people in the Q-Chem office, especially Xintian and Shannon, for helping me know a lot about C++ and getting familiar with the Q-Chem infrastructure. Lastly, I thank you all for listening, and I'm happy to take any questions.
That was a wonderful talk. Thank you so much. We have one question, two questions already. So the first one is, I think this was asked sometime around slide 29-ish for context. There we go, perfect. The question is, does one need a MBD correction for these types of calculations?
What? Sorry.
A many body dispersion correction, I think, is what that, I think that's, yeah.
Right now we haven't implemented that.
Okay.
So our tight binding Hamiltonian is just made to match the frontier orbital of the molecule so that it can have some charge transfer characters. So we we did those empirical calculations just to do a proof of concept. So we haven't considered that.
Okay, perfect. Thank you. And then we have another question, which is the constrained CASSCF code already available in Q-Chem 6.3.1? And is any dynamic correlation on top possible?
Right now I haven't merged my trunk into the Q-Chem trunk, so it is not available for people outside our group, but I hope I will do it as soon as possible. Like for dynamic correlations, I feel like the idea of constrained CASSCF is to provide a good set of MO orbitals. So of course we can use do some CASSPT2 calculation or CCSDT using this set of MO orbitals, and I think that is a very good direction to go.
Excellent. Thank you. I will mark that as answered. And then we have another question, which is, will this support periodic systems in the future? Well, they haven't said in the future. They just said, will this support periodic systems? So, but yes.
I think this concept would also apply to a periodic system, but apparently we haven't merged that with the QCAN QCPBC code. Yeah.
Yeah. So it could be applicable to that though. So that's
Yes.
an exciting future potential new direction for this.
Yes.
So yeah. So thank you. Do we have any other questions? You can post them either in the chat or in the Q&A at the bottom here. Great. Well, if nobody else has any questions, if anyone thinks of them later, if you wake up in the middle of the night realizing I forgot to ask something, there will be a forum thread available for you to post any follow-up questions on. And thank you again to Xinchun on a wonderful, successful webinar. It's been really cool to see this work as you've been working on it in the office, and then as it's kind of come to fruition, as you've been working on it back back in the Subotnik group. It's been very cool to see all of this actually come together very nicely into sort of this nice final product that you've presented. And thank you again for all of the work that you've done. It was wonderful having you here in the office this past summer. So thank you so much. And without any further ado, again, this will be, I posted this in the chat, but this will be posted on our YouTube channel, hopefully within the next week or so. And I appreciate everyone's attention, and thank you again to Xinchun for a wonderful summer and also a wonderful webinar. So thank you. Have a wonderful afternoon, everyone.